Hello dear students, we are back with the acid-base concepts, but this time with respect to the theory given by the scientist, namely Lowry and Bronsted. And so this theory is also known as Lowry-Bronsted acid-base theory. In the earlier episode, we had gone across the Arrhenius acid-base concept, where we had come across the limitations for few compounds like ammonia, NH3, and sodium carbonate. That you could have come to the conclusion that ammonia is a base, but according to the concepts of Arrhenius, which couldn't release OH minus, were not a base. So ammonia, sodium carbonate were not considered to be a base, even though they were a basic compounds. So there was some modification given by Lowry and Bronsted, and they changed the concept of acid and bases. What was the change? Let's see. According to Lowry and Bronsted, a compound, if loses a proton, H plus, then it is an acid. No problem. And a compound, if it, interesting, gains a proton, then it's a base. So according to Lowry-Bronsted, the concept for losing OH minus was further no more. They just concentrated on the proton, and that's why this theory is also named as proton transfer theory. It is also known as proton transfer theory. Why? Because a compound, if loses a proton, is an acid, and a compound, if accepts a proton, it's a base. Simple, they made the theory. This was around 1923 or so, and according to them, we can just consider a few examples according to their theory. Suppose if you consider HCl and react it with water, as we did it for Arrhenius, right? What will happen? It will form H plus. That H plus will combine with H2O, and that will convert into H3O plus, and another, on the other hand, we will have a chloride ion Cl minus. Now these two can recombine and they can form HCl and water respectively again. So this is how the equilibrium will be set up. That is not the point. The point is which of the two is an acid. Okay. Now if you consider HCl and if you consider water, out of the two, which compound you think has lost a proton? Obviously it is hydrochloric acid. So this is your acid. So obviously it has lost a proton, so it's an acid. So what is the theory? If a compound gains a proton, it's a base. So over here you can see water has got oxygen, and oxygen has two lone pairs. So it will have a tendency to accept H plus easily. So it gains a proton, and that's why you can see this is your base. So in presence of HCl, water is a base, and you know water is amphoteric in nature. It can act both acid as well as base. We'll talk about that as well. Now get on to this side. Out of these two, which do you think now can lose a proton? This doesn't have a proton, so obviously this is rich with proton, it can lose a proton. So over here, out of these two, again I would say this is an acid. So obviously Cl minus has to be a base. Now you are confused. This is acid on the left hand side, this is acid on the right hand side. How can we, differentiate between the two? Okay, fine, no problem. This is your original acid. It has formed H3O plus by losing its proton to water. So this is your acid, but now it can be named as conjugate acid. So if you are asked that if acid and conjugate acid is to be distinguished in this reaction, you can now easily make it into simpler part that HCl is acid, but its conjugate acid is not HCl, but it is H3O plus. Similarly, if H2O is a base, you can see it's a base, then its conjugate base is Cl minus. So this is how the things have been simplified, saying acid, base, conjugate base. One more. If I consider nitric acid, HNO3, and react it with water, again nitric acid will form proton H plus, and that will be accepted by water molecule. So that will convert into H3O plus, and it will form NO3 minus, that is nitrate ion. So again here HNO3 has lost a proton, so it's an acid. Water has gained a proton, so it's a base. Forgetting the left hand side, let's talk with respect to the right hand side. H3O plus will have a tendency to lose a proton, and if it loses a proton, it's an acid. So it is an acid. And on the other hand, NO3 minus will have a tendency to gain a proton, and according to if it gains a proton, it's a base. So over here, this is a base. Simple. Fine. Okay, now see. I am taking H2O and I am reacting it with ammonia, NH3. As you know, it was the limitation for Arrhenius theory, so I am taking it over here. Now interestingly, you can see water will lose a proton. Why? Because nitrogen has a lone pair, and so it can easily accept a proton. See, I said earlier, water is amphoteric in nature. It can act both acid as well as base depending on the compound to which it is reacted. Over here it's ammonia, and you know ammonia has got originally, if you consider the laboratory aspect, it has got the basic characteristic. So when it reacts with water, water will have a tendency to lose a proton. As it loses a proton, water is, I have categorized under acid. On the other hand, ammonia, NH3, will have a tendency to gain that proton which is lost by water. So one which gains a proton is a base. So I have categorized it under base. Okay. What it forms? Water loses a proton, so it forms OH minus. I'll write it over here. And NH3 will gain a proton, so it will form NH4 plus. Now out of these two, which will act as an acid? So obviously one which is rich with proton, only that compound or that ion, what you can consider, will have tendency to lose a proton. So NH4 plus loses a proton, and that's the concept that it is an acid. But already this is an acid, so it is considered to be its conjugate acid. On the other hand, OH minus will have tendency to gain that proton. So OH minus is categorized as a base, but already a base is ammonia, so this is a conjugate base of ammonia, you can consider so. So this is how you can characterize an acid and a base without any difficulty with respect to the Lowry-Bronsted acid-base theory. So this theory is again given, recognized with different names. As I said earlier, it's based on only proton exchange, so it is also known as proton transfer theory, proton exchange theory. Moreover, it also forms conjugate parts, so it is also known as conjugate acid-base theory. So many a times it is asked in different forms, not as simply as Lowry-Bronsted, but maybe proton transfer, proton exchange, or even conjugate acid-base theory. Then in both the cases or all the cases, you need to consider it as Lowry-Bronsted acid-base theory. Same you can consider for sodium carbonate, Na2CO3, and react it with water. Again water acts as an acid, loses a proton, so that will form OH minus as it loses a proton. Now that O of carbonate, CO3, that is oxygen, will attract the H plus from water, and that will form Na2 HCO3. Now that H has come with a plus sign, so that is Na2H plus CO3 ion. So this is your conjugate acid, this is your conjugate base. So now according to Lowry-Bronsted theory, the previous problem of Arrhenius theory with respect to ammonia and sodium carbonate can be overcome, and that's why we say that this is the modified version of Arrhenius theory. I hope you have understood the limitation of Arrhenius, and with respect to that, the Laurie-Bronsted theory. I'm going to discuss this Laurie-Bronsted theory in the next episode with respect to some different concept of its conjugate acid and conjugate base part. How can you recognize the conjugate acid and conjugate base for any compound as far as Laurie-Bronsted theory concerned. Till then, prepare well the concept and come prepared for the next episode again for Laurie and Bronsted. Till then, goodbye.